محوطب والنيبن. Hello everyone. So in this series of videos I will be assuming you have some background, calculus, differentiation, integration, some familiarity with Newton's second law. This is typically at the level of a first or maybe a second year undergraduate physics curriculum. I also have written an article with the full derivation, which I will leave in the description box below, just in case if you prefer reading over watching videos. And with that in mind, let us begin. So let's start by a comparison between the classical and the quantum. The main equation in classical mechanics is Newton's second law. It's a causal relationship between forces and motion. Force is the cause, acceleration is the effect. Given the cause, we can predict the effect. Suppose we have a particle of mass m initially located at some position r0, and maybe having some velocity v0 as well. If we know the force acting on it at that moment, the cause, we can calculate where it will be a little bit later. So in this example, the force pulled the particle a little bit towards it. We can then repeat the process again after having the particle position at the time t0 plus dt. And we have the new velocity v at t plus dt. And we have the new force. And then we have a new position for our particle. And so on. So we can connect all the dots to get the trajectory of the particle, which is the position as a function of time. Here, the state of the system is described by the position of the particle at any moment of time. So this represents the state of the system. Of course, the system here being only the single particle we have. We can rewrite Newton's second law in a little bit more explicit form that shows the dependence on the state of our system. So we can recall that the acceleration is the second derivative of position with respect to time. And then Newton's second law becomes f of t is equal to m times the second derivative of r with respect to t, which is a second order differential equation that can be solved for r as a function of t, and then we know all the information about the system at any moment of time. In quantum mechanics, we have the Schrödinger equation as the main equation. Although it doesn't look like one, it is a wave equation, and we will see later that we can derive it from a standard wave equation. U here is the speed of the phase, not the speed of the particle, which will be an important distinction we will make later on. So Schrödinger's equation really describes the propagation of a wave with phase speed u. Now the wave function, psi, as a function of position and time, is the amplitude of the wave at any location and any time. Given the initial profile of the wave, the Schrödinger equation describes how that profile evolves and what it will be at a later time t plus dt. This is the analog of the classical mechanics trajectory. Okay, now, what does a wave equation have to do with the motion of a particle? Well, that's exactly the point of Schrödinger's paper and Louis de Broglie before him. Particles are wave. They don't just behave like waves, they are matter waves, at least according to Schrödinger and Louis de Broglie. The reason why we see those waves behaving as small concentrated blobs of matter is superpositions of waves. I will discuss that in later videos, but for now let's proceed a little bit with the Schrödinger equation to have an idea of what our path will be. Now, for conservative systems where the interactions are time independent, we have the potential energy is only a function of position. Then the wave function could be separated into a spatial part and a time part. And if we substitute that into the time-dependent Schrödinger equation that we wrote above, we can derive the time-independent Schrödinger equation, as we will see. Now divide both sides by psi times phi. The left-hand side is a function of t, while the right-hand side is a function of r, so if they are both equal, then each of them individually has to be a constant. We can call that constant E, just because we know it will turn out to be the energy, but you can call it anything else and then figure that out later. This decomposition decouples space from time, so we have two equations. The first equation is easy to solve. I can multiply both sides by dt and I rearrange the equation like that. Then integrating both sides, I get the left-hand side is the natural log. Then we can exponentiate both sides to get phi as a function of t all by itself. And then the constant can be just absorbed into the full solution. We can drop it out without any loss of generality. The other equation, the spatial equation, is what's known as the time-independent Schrödinger equation. We can multiply both sides by psi to get it to the standard form. The full wave function will be the product of these two. My main target in this series is to show how Schrödinger derived the time-independent equation, and then how he generalized it to the full time-dependent version. But to do so, we need some background, and that's what the next videos are all about. We will briefly review some of the formulations of classical mechanics, starting with a very brief mention of Newton's second law, and I guess we already did that here, so we might not need to do that in the next video. Then we will introduce the action principle, from which we will derive the Euler-Lagrange equations, the Hamilton equations, and finally, and most importantly, the Hamilton-Jacobi equation. The Hamilton-Jacobi equation is the starting point of Schrödinger's derivation. Because it's not really covered a lot in mechanics classes, I will devote some of the time discussing how to get it from the more familiar Newton's second law. Only then we will be able to proceed with the derivation of the Schrödinger's equation. If you are already familiar with all of this, you can skip these videos and watch the derivation video right away. Alright, see you in the next video. Ujai.